NASA STEM Engagement and Educator Professional Development Collaborative logo. Welcome to NASA STEM EPDC Quick Bits Big Ideas in Science Content. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world, and finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
NASA STEM EPDC Specialist, Dr. Barbie Buckner, NASA Goddard Space Flight Center. Today's big idea in science that we are going to highlight is called sound effects. We will have students building using the engineering design process to both amplify and reduce volume. As part of the sound effects activity, students will learn about the principles of sound, specifically how to amplify and reduce volume. Students will use the engineering design process to construct a speaker to amplify the sound, and then they will be challenged to find a solution to reduce this perceived sound volume. But before we get into the activity, what is sound? Sound is one of the many forms of energy, and it's produced by vibrating objects that travel from one place to another through vibrating material, such as solids, liquids, or gas. This matter sound travels through is called a medium. Sound travels in the form of invisible waves called compressional waves. Unlike water waves that move up and down, sound waves move toward or away from a source, and these repeated compressions are then spreading out through atoms and molecules of matter. Humans have a normal range of hearing between 20 and 20,000 hertz, which is different from many other animals, as you can see on this chart. We measure the frequency of sound waves or pitch in a unit called hertz, named after the first person to provide conclusive proof of the existence of electromagnetic waves. Since sound waves spread out as they travel away from the source, the sound intensity decreases over time, which means that the farther the listener is away from the source, the quieter the sound is. Sound is something that most of us take for granted, and rarely do we even consider the physics involved with it. It can come in many forms: voice, machinery, musical instruments, computers, but all are transmitted in the same way, through vibrations. In the most basic sense, when sound is created, it causes the molecules nearest to the source to vibrate. As with any energy transfer, each time a molecule vibrates, a little bit of the energy is transferred, and that's what causes the sound over time to get quieter with distance. And that's why also, with louder sounds, there is a lot more vibration. This is why at, say, a rock concert, you can literally feel the bass notes vibrating inside yourself. These molecules of your body are vibrating and allows you to physically feel the music. Now, the human ear is an amazing instrument for capturing sound, and it all has to do with vibration. The visible part of the ear is shaped to catch the sound wave as they travel through the air. When the vibrating air molecules hit the eardrum, it starts to vibrate, and that vibration is passed through the small bones of the inner ear, better known as the hammer, the anvil, and the stirrup. And these vibrations on these small bones are then passed on to the cochlea, which contains a fluid. As the fluid vibrates, hair cells change the vibrations to electric signals that travel through the auditory nerve to the brain. Your brain then understands these electrical signals as sound and determines what these sounds mean and how to respond. In thinking about the loudness of sound, that's really more of a human perception, as opposed to a scientific quantity or property. As you can see from this graph, a car door slammed at your neighbor's house may be perceived at 60 decibels, while a gunshot up to 130, 135. You'll see at 105, kind of bolded there, the Concorde sonic boom or nearby thunder. Here at NASA, we are taking a look at the sonic boom and doing sonic boom research. In particular, we have a new X-plane called the X-59, and it's looking at a way to design a new flying profile that would allow the sonic boom to be more of a sonic thump. As a matter of fact, let's take a look at a video.
This video highlights the low-boom flight demonstrator, better known as the X-59. The great aviation transformation begins now as NASA moves ahead with the development of an X-plane designed to demonstrate low-boom technology and promote regulatory change for commercial supersonic flight. NASA wants to reduce the impact of the boom in supersonic flight and make traveling beyond the speed of sound more common.
So what exactly is that? That's NASA's newest X-plane, the X-59, currently being built in Palmdale, California by Lockheed Martin. It's designed with quiet supersonic technology, and it's intended to open up a new era of faster than sound air travel over land. And part of that is by reducing the sound of the sonic boom to more of a sonic thump. But what exactly is a sonic boom? As an aircraft travels at the speed of sound, it begins to overtake the sound waves which pile up in front of the aircraft. And when that aircraft moves faster than the sound waves can travel, the masked shock wave is formed, creating a sonic boom which can be heard on the ground. That sonic boom is a loud thunder-like noise heard by the person that's on the ground when an aircraft flies overhead at supersonic speed. Air reacts like a fluid to supersonic objects, and as objects travel through the air molecules are pushed aside with great force. So NASA has studied and is testing devices that can be used on aircraft to lessen this noise and window rattling effect of supersonic flight. If we can do that, there's a chance that commercial planes could then fly supersonic. Right now, commercial planes aren't allowed to fly faster than the speed of sound over land because they would currently create sonic booms which are loud and disruptive to both humans and animals. But with the X-59, again, NASA's newest experimental aircraft, there's a potential that we could eventually lead to supersonic commercial aircraft that could travel much faster than the current subsonic commercial aircraft, saving people time in the air. Currently, a subsonic flight from LA to New York takes approximately 5 hours. With supersonic, it could be cut in half to 2.5 hours. That's right, supersonic travel over land would cut travel time in half. Now that we've taken a look at what NASA's doing about that with their research, let's take a look with an activity that you can do. The required materials are a paper towel tube, disposable plastic cups, scissors, tape, and a smartphone. Some other miscellaneous materials would be additional plastic cups, different types of paper, cardstock, cotton balls, or other household items that you might have lying around that you decide that within your engineering design process you'd like to use. But I'll let you know when that opportunity is for you to use those miscellaneous materials. For now, let's talk about the two different parts of the activity. The first part of the activity, you're attempting to increase or amplify the sound that you hear. You will need a smartphone, a paper towel tube, 2 plastic cups, scissors, markers, and tape if you like. For the second part of the activity, you'll need the design that you created in the first part to amplify, but you'll also need those miscellaneous materials. And I say the miscellaneous materials, use what you have around the house. Let's start now that you've got your materials together, is to grab your paper towel tube and you want to trace the speaker part out on the phone in the middle. And you can see here that I've done that, and that's basically the profile of my phone. And then what you'll do is you will cut that shape out and make sure that the phone comfortably fits into it so that you can take it in and out. Please have an adult help you. After you've done that, you'll use the end of the paper towel tubes to mark on the 2 cups so that you can then place the paper towel tube into those cups. You can experiment with where you place the holes. You can see here in this picture, the holes are very close to the back of the cup. But then in this picture, you can see that the holes that we've cut are about the middle. And so one of the things that we'll talk about is using the engineering design process as a means for doing your activity. Here's an example of what one might look at. There's several different versions out here, but this is from NASA's Best Activity Guide. And what they do is they have it broken down into several different steps. Ask, which is to identify and define the problem. Second thing is to imagine, brainstorm solutions and research ideas. I've already mentioned about where you place the paper towel tube into the cup could make a difference. Plan, select and sketch a design. Create, build a working model or prototype. Test, collect data and evaluate the solution. Improve, optimize and redesign the solution. Now remember, when you're optimizing and redesigning, it's important to only change one item at a time, because if you change multiple items and then test, you don't know which item either caused a change or didn't cause a change. So when improving and retesting, make sure it's one item at a time. And repeat this process. And then ultimately at the end, we want to share out the results. We're going to take the phone and insert it into the cutout area of the paper towel tube. And in doing so, you should be able to tell a difference from the sound coming out the bottom of the phone versus coming out the paper cups. And so what you'll want to do is, like I said, use that engineering design process, change different items, change how far the paper towel tube is in or out, change the direction at which those cups are angled. Any aspect of change that you want to do. Look at different ways that you can help make the sound louder. Now, we're not going to get fancy and get out some device to measure how many decibels it's reading. Use your perception to hear what you think is louder versus what you think is quieter. Now, once you've optimized your design, then we can go on to part 2. You'll take your device, and this is where you'll use those miscellaneous items. And again, you don't have to use all of these, and you can even add items that aren't even listed or shown here on the screen. And again, with each item that you choose to use, remember, use the engineering design process. Remember that when you improve, it's only one item at a time before you retest it. Loud sounds are desirable in some cases. If you'll think about burglar alarms or police sirens, or maybe even a ping on a medical equipment, and most definitely on an alarm that wakes us up in the morning so that we're not late for school. Other times, loud noises can be potentially hazardous to health. We don't want it to hurt our ears, or sometimes unwelcome noise. And that's a lot of time the case with the engine noise of an aircraft. NASA for years, decades even, has been studying aircraft noise in order to reduce the impact by using chevrons. And when we say chevron, we're talking about this zigzag area, the back of the engine. And NASA has done research to find that that helps to reduce the sound of the aircraft engine. You can also think about other things within our life that help to quieten noises. On our cars, they're called mufflers. And the simplest way of reducing noise is to reduce the number of molecules available to vibrate. In a vacuum, for example, there's no air molecules to vibrate, therefore there is no sound. But another way is to control the amount of time it takes to reach our ears. Remember, we talked about the longer it takes, the quieter it gets. The muffler of a car's exhaust, for example, uses baffles to increase the distance that the gases have to travel. as well as constantly changing the direction with each turn, further reducing the energy available for noise production. But you can also see that with motorcycles, the muffler is much smaller, so it's difficult to have as many directions or as much distance for it to travel. So with motorcycles, they use tubes that make it harder for the sound to escape. And when it eventually does, it is predominantly absorbed by the padding around it before being released into the atmosphere. Now remember, in decreasing that sound, the sound still has to get through. You can't just take a wad of paper and shove it in there and there not be able to get any sound out. If you'll think about flying with an airplane or even driving a car, the gases still have to escape through the engine. Don't cut off all the air that's there. Remember, you still have to have some that flows through. In using the engineering design process, use a systematic step-by-step way to choose one option at a time, so that as you explore today's big idea about sound effects, you can find ways to both amplify and reduce volume.
Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links. www.txstate-epdc.net. Logos for the Texas State University LBJ Institute for STEM Education and Research, NASA STEM Engagement and Educator Professional Development Collaborative, and NASA Partner. The material contained in this document is based upon work supported by a National Aeronautics and Space Administration, NASA, grant, or cooperative agreement. Any opinions, findings, conclusions, or recommendations expressed in this material are those of the author and do not necessarily reflect the views of NASA. Images and footage courtesy of NASA. Images and footage used under licenses from Shutterstock.com and Envato.